Okay, so in this segment, we're going to talk about reaction thermodynamics. And just to remind you what a reaction is, we start with reactants. I'm going to try to write with this pen. So I think before we wrote A plus B, and then we have an arrow. That means bonds are made or bonds are broken or both. And then on the other side of the arrow, on the pointy side of the arrow, that's where we put the products. So you probably remember that. All right, I'm going to erase that though because it's in the way. Okay, so you see that. So when we talk about reactions, that's what we're talking about, okay? So during the course of a reaction, bonds are made and bonds are broken. So energy is put in and energy is released out, or one or both. So what we are looking at when we talk about reaction thermodynamics, we usually think about reactions as being either reactions that require an input of energy, meaning bonds are made, or reactions that release energy, meaning bonds are broken. So just simplifying things right now and kind of treating reactions in a very binary way. Either the reaction makes bonds or the reaction breaks bonds. So let's treat it sort of in those two categories. And we're not going to get any more complicated than this anyway. So when a reaction builds something, so anabolic reactions, energy has to be put in to make a bond. And so on these charts here, this is the progress of a reaction on a graph. And they used a bar graph, but I'm drawing a line to connect the reactants and the products. The progress of the reaction is time. That's the x-axis. And then the energy level of the molecules is on the y-axis. It's called free energy. And free energy is given the letter G in thermodynamics, named after Gibbs. That's a guy, Dr. Gibbs. So Gibbs free energy, G is free energy. So energy. So during the progress of a reaction, you start with some reactants, and then if you're building bonds, you have to put energy in, and the products then have bonds that weren't in the reactants. So there's more energy in the products than there were in the reactants. And if that's true, that means energy must have come into the system from, let's call it the universe. So energy has to be put in to build those bonds. The other possibility is that you have a reaction in which the reactants are being broken down. Bonds are being broken. And so the reactants have energy in their bonds, but once those bonds are broken, the energy is released into the universe, and the products don't have those bonds anymore, so they don't have as much energy. And so in that reaction, energy has been released. So I'm kind of connecting these, I'm making these lines on purpose, because what we're saying is that when there's a building reaction, this would be anabolic up here, then energy had to be put in to build those, to make bonds. We call this reaction an uphill reaction. We call it energetically uphill because when we connect the energy level of the reactants and the products, we see this increasing slope. And that's because energy has been put into the system from somewhere else. On the second option, if you have a different reaction and reactants are being broken down, bonds are being broken, then the energy in the bonds is released out to the universe and the products have less energy than the reactants. So we call this reaction energetically downhill. And so this would be catabolic type reactions. So if we're kind of using our same categories that we mentioned before. So breakdown reactions are energetically downhill, building reactions are energetically uphill. Anabolic reactions require energy to be supplied. Catabolic reactions actually release energy out. And we use this G, or delta G, the change in energy, as another indicator of this same concept. So in an anabolic reaction, if you look, the products have a larger amount of energy than the reactants. So the change in G, the change in energy over the course of the reaction, is equal to the energy of the products, or sometimes we say G final, in this case G products, minus the energy of the reactants, G initial. Anytime you have a delta calculation, it's always going to be the final number minus the initial number. And so this is a standard way of doing this. So when we take the delta G, if we are taking the delta G of any anabolic reaction, because the products have more energy than the reactants, when you do the energy of the products minus energy of the reactants, you still have a positive number. And so we say any anabolic reaction has a delta G value that is greater than 0, a positive number. However, in any catabolic reaction, the products G final is always going to be less than G initial, or G products is always less than G reactants. And so when you take a small number minus a larger number, you'll always get overall your delta G number will be a negative number, and that's expressed here. Delta G is less than 0. So these are all characteristics of anabolic reactions. So all of these are all characteristics of anabolic reactions. Anabolic reactions are building reactions. They're always uphill reactions. The products always have more energy than the reactants because energy has been put in, and the delta G number is always a positive number. So those things all go together to describe those kinds of reactions. The other possibility in our binary kind of description of this is that catabolic reactions are the opposite. The reactants have more energy than the products, therefore that means energy has been released to the universe. The delta G number is always a negative number, and so those characteristics go together. Okay, so I summarize that on this next slide. And we've added some terms, all right? So this term is endergonic. Endergonic goes with the anabolic reactions on the previous slide. So anabolic reactions are endergonic. They always have a positive number for their delta G value. Their products always have more energy than their reactants. There has to be an input of energy, therefore, during the reaction. The reaction goes uphill, and it includes synthesis and building reactions, anabolic. So those terms, all those features and terms are all part of that story. The other type of reaction, the flip side, would be called an exergonic reaction. That's going to be catabolic reactions. All catabolic reactions have to have a negative delta G. Products have less free energy than the reactants. The reactions release energy into the universe. All exergonic reactions are downhill, and that includes breakdown reactions of various types, like hydrolysis, digestion, or other breakdown reactions. So you end up with these like two buckets, these two types of reactions, and I'm going to give you on the quiz and on the test, if I tell you that you have a reaction that has a positive delta G, then I could ask you, is this endergonic or exergonic? Well, just based on that information, it has to be endergonic because that's the bucket that you're in. When you think about positive delta G, you think endergonic. Or I could say a reaction has a positive delta G. Is this uphill or downhill energetically? Or it has a positive delta G. Does this reaction require an input of energy, or does it release energy? So if I give you a piece of information from the top half of this slide, all of the characteristics will go along with that. If I give you a piece of information from the bottom half of this slide, all of those characteristics go with that. Okay, so these are your two types of reactions that we're considering: breakdown reactions and building reactions. Okay, so here's where I'm going with this. What a cell actually does, because no reaction exists in a vacuum, the reactions are happening in a cell, and the cell is managing the energy that is being released and put into different reactions. So lots of different reactions happening in a cell. And so a cell will, what we call, couple endergonic reactions with exergonic reactions. So what I'm saying is, what a cell does, when a reaction is exergonic, let's say it's releasing a certain amount of energy, let's say 10 units of energy. What the cell will do is that energy is released, but the cell can then direct it into an endergonic reaction, which requires 10 units of energy. So 10 units of energy are released from an exergonic reaction, and right next to it, there's an, excuse me, I said that wrong. 10 units of energy are released from an exergonic reaction, and right next to it, there's an endergonic reaction that needs 10 units of energy, for example. And so the energy released from one reaction is then absorbed or put into a nearby reaction or the next reaction. And so this is called coupling. It has to be the coupling of an exergonic reaction with an endergonic reaction. And there has to be enough energy released from the exergonic reaction to satisfy the requirement of the endergonic reaction. Typically, there's a little bit more energy released than what is required. So let's say 10 units of energy are released from an exergonic reaction, and 9.5 units of energy are needed by this endergonic reaction. Then that can be coupled, but there would be a 0.5 units of energy left over, and that's lost as heat. But the cell will try to couple things together as best it can to conserve and to really manage that energy well and not lose too much as heat. Sometimes it's more successful than others. All right. So when a reaction is exergonic, it releases energy, and that energy is coupled to an endergonic reaction. And that way, the energy transfers from one reaction to another reaction with a small loss of heat typically in the process. And that was part of, remember, our first law of thermodynamics is that no energy transfer or coupling is completely efficient. There's typically a little bit lost as heat. So you just have to accept that. All right, so we're gonna look at this molecule in particular. We've been talking about energy very generally. We've been talking about covalent bonds, hold energy. We've been talking about radiation is energy. But we need to talk specifically about this particular molecule. It's called ATP, which is an acronym for adenosine triphosphate. And adenosine triphosphate is really a molecule that has more than one purpose in a cell. In this chapter, we're talking about it in the sense of it being what we call the energy currency of a cell. ATP is also one of the building blocks of nucleic acids. If you look at it, it has the components of a nucleotide, the ribose, the nitrogenous base called adenine, and then phosphate. But in this chapter, we're looking at the function of ATP as an energy molecule. So it has this dual function. And so ATP as an energy molecule is what we're focusing on here. And ATP, the T stands for triphosphate. It has 3 phosphates. So you probably remember your functional groups. Here's phosphate here, here's one here, and here's one here. They're all linked together now by this point in a dehydration synthesis process. But there's 3 phosphates there. And the bonds between the phosphates Those are covalent bonds, and they particularly have a high amount of energy, those particular bonds. And so we call them high energy bonds. And so the cell, when the cell has a reaction that releases energy, what it will typically do is couple that release of energy with the synthesis of ATP. So the energy that's released from an exergonic reaction is then put into an endergonic reaction. And in particular, the endergonic reaction is the building of ATP. You see how ATP here is the product? The building of ATP, which requires 12 units of energy. Okay? So when a cell has an exergonic reaction, it can capture that energy. It can build a molecule of ATP. It will. If a cell then later needs energy for some other reaction to happen, it can break that same ATP down, and that will release 12 units of energy. And that energy can then be coupled to some other reaction that needs 12 or less units of energy. So ATP is kind of the key, it's a key molecule as part of these energy transfers. ATP can be built, can be made from its component pieces, which are called ADP, adenosine diphosphate. That would be adenosine with 2 phosphates only. And then one more phosphate. When that is joined together, that's a building reaction, and that requires 12 units of energy. But then the exact opposite reaction, you start with that ATP, that last phosphate is broken off, and that releases 12 units of energy. And so by taking ADP plus phosphate and joining them together, that molecule then holds 12 units of energy, and then when that phosphate is broken off, it releases 12 units of energy. And so for that reason, we say that ATP is the currency of the cell in terms of its energy. It's holding energy and then releasing energy on demand. So the cell prefers to use ATP for this purpose. Other molecules come into the cell that have energy, but what the cell likes to do is then pretty quickly transfer the energy from those molecules into ATP. And then when it needs energy, it breaks down ATP to get the energy back out. So we call this the currency of the cell. In the same way, when you go to a foreign country and you have your US dollars, but you go to a different country and they want to use some other type of currency, you have to go to that little window and trade your money in, and they give you the currency for that country. In the same way, when a cell takes in energy in different molecules, it likes to then transfer that energy into ATP form. And so that's what happens in the cell, that ATP becomes that key, that currency that the cell prefers. All right, so we're going to break here, and then we will finish the rest of the lecture. We're going to talk about enzymes and enzymatic reactions for the next lecture segment.